Good morning and welcome back to Algebra 1 with Miss Betsy. Today we're starting chapter 2 in our book, and we're going to be talking about real numbers. Specifically in section 2.1 we're going to be talking about kinds of numbers. So if you want to be able to follow along with your textbook, we are in Algebra 1 for Christian schools. We're using the second edition, and it is published by Bob Jones University Press. Third edition is not directly compatible, though the material is the same. You'll have to find it in a different section. And is there any reason at all that you have to use text to follow along and gain from this video? Not at all. You can learn about different types of numbers regardless of what text you're using. So let's pray and then we'll go ahead and get started. Father, thank you for your goodness to us, and thank you that you love us. I ask that you would help us today to be careful to listen for your voice and to be diligent to do those things that you direct us in. Father, help me to communicate to the kids today, or to the adults, and would ask you to help them as they work through their problems in the process of understanding new material. And we thank you for your presence with us. In Jesus' name, amen. Okay, I have a lame joke for you that I had never heard before, and you know what? It seems to me that that's exactly what I said on the last video that I did, that it was one I'd never heard before. So let me think, because I really don't want to re-record this video. Okay, I think I gave this one to a pre-algebra video. Why did the girl smear peanut butter on the road? Well, if you live in a major metropolitan area, you can certainly relate to this one. The girl smeared peanut butter on the road to go with the traffic jam. If you're following along with me in the second edition of Algebra 1, we are on page 46 today. Now, we're going to be classifying different types of numbers in much the same way that if you've had biology or zoology or something like that, we have a classification system where we go through describing specifically what a particular plant is, or a particular animal, or a sea creature, and it involves Latin names, and you start off with this great big ginormous group, like mammals, and you can track down until this tree narrows, and you have the specific type of cow that you're talking about. And you have similar things that you can do with food. Perhaps you wanted to start with food, and that included everything that you were eating. And maybe you wanted to divide it into unhealthy food and maybe healthy food. Well, there are a variety of different types of healthy foods. There might be meats, there might be vegetables, and then we have fruits. Well, with inside meats, maybe you have beef, and maybe you have, I'm going to call chicken even though it's a poultry. But you get the point. You just continue breaking downwards, but way up here at the top is the huge overarching category that describes all of the food. Well, you can do a similar thing to that with our number system. Instead of saying food, though, the largest category that we have are the complex numbers. That's like our category of food. Complex numbers. And they describe that with a C. And you have two main divisions that our numbers break into. And kids, you are just going to laugh at this and say, you have got to be kidding me. Not kidding you. We have real numbers and we have imaginary numbers. I don't think I spelled that correctly. I don't believe I did. Imaginary numbers is what we called them when I was growing up, but they're complex numbers. Imaginary numbers. Now, complex numbers, imaginary numbers, we don't talk about them at all in Algebra 1. You won't get those until Algebra 2. So we're only going to be worried about the part of the numbers, only be concerned about the part of the numbers that includes what we call real. numbers. And these have two basic breakdowns here. You have rational numbers, and then you have irrational numbers. And rational numbers are anything that can be written as a ratio. And a lot of this is just vocabulary. It's all in your book, and we're going to talk about it some more. Underneath the rational numbers, then you have integers. Then you have whole numbers. Then you have natural numbers. And these are the types of numbers that you're going to need to be able to identify. Remember, complex and imaginary numbers we're not going to be talking about at all in this class. Now, it's sort of like a script R. If you see a script R, that means the real numbers. Now wait until you see what they use for a rational number. Now I'm not going to do a script Q because it looks sort of like a 2. But Q is what they use for the rational numbers. I have no idea why they use the Q, and I haven't looked it up. You just need to know that the rational numbers are Q. The integers, when I was growing up, they were just I. Made a lot of sense. I is for integer. Now it's a script Z, indicates the set of the integers. Then finally we come down to where it makes a lot of sense. We say W is the whole numbers, and N represents the set, which is the natural numbers. Now this just goes from the biggest group down to the smallest group. Natural numbers we've referred to a lot already. Natural numbers are the numbers that you naturally learn how to count. Mom and Dad don't start you off going 0, 1, 2, 3, 4, 5, or 0, 1/3, 2/3, 1, 4/3. They don't go start you off counting like that, do they? You naturally count 1, 2, 3, 4, 5, 6, 7, 8. That's what the natural numbers are. The whole numbers, you're going to add a 0. So the whole numbers are going to be the natural numbers plus 0. 0, 1, 2, 3, 4, 5, and there's no end. You can have those whole numbers goes far, they never stop going in the positive direction. I'm doing this because this is on the positive side of the number line. And then we have the integers. What are the integers? They're the whole numbers plus the opposites of our counting numbers or our natural numbers. So that they're the -1 on the number line, your imaginary number line that you can see in your head. -1, -2, -3, -4. That pattern continues forever in the negative direction, and 0 in the positive direction on the number line. That's what the integers are. Rational numbers are anything that can be written as a ratio of numbers. Irrational numbers can't be written as a ratio. Now, specifically for some of my parents right here in my local co-op, don't get bent out of shape trying to get these exactly correct and the technical definition for them right now. As the kids work with these, they will easily and quickly learn what all of these different types of numbers are. But we are going to talk about them some more today. Up until this point in our class, we haven't done much to review fractions, and all of you coming into this class should be very comfortable with fractions, but I know that some of you aren't, so we'll be doing some review time, and the book schedules that. But fractions are actually rational numbers, and this is what a rational number is. Remember, I had that chart that I wrote, that list. You can actually find that list at the top of page 46. Rational numbers are expressed as a ratio of two numbers, rational numbers. As a ratio in one way to express a ratio is it looks exactly like a fraction. That's a ratio of 1 to 3. This is a ratio, 2 to 7. This is a ratio, 4 over a negative 7. Here's another ratio, negative 3 over negative 2. Ratios look very similar to what your fractions are. You might even call them a fraction. It's just that probably when you were in elementary school, you did not include integers. Remember, integers are the positive and negative sign numbers plus 0. Your fractions probably didn't have negative numbers in them, but that's what a rational number is. There is one specific thing that that might look like a ratio that doesn't work. What about this? If you have 3 pieces of candy and you're going to divide, can you divide them into 0 groups? Well, you have to eat them, I guess. But no, you cannot divide something by 0. We have a fancy way of describing that, of defining that in math, and we say that division by 0, the answer is not 0. We say division by 0 is undefined. So a rational number can be expressed as a ratio of two numbers, but the denominator, I'm looking for a different color pen. The denominator has to be different from 0. May not be 0. You could write this just using variables. A rational number can be written as a over b, but b cannot be equal to 0. So you see these examples here of rational numbers. This is not rational. And a rational number, you see the root here, ratio. Rational numbers are ratios. What about this number here that I have not illustrated for you yet? What about one that is a mixed number? What if we had 4 and 2/3? Is that a rational number? Take a second and think about that. Oh my coffee is very hot. Well, this part of it's a rational number, but that's not. It says it has to look like a fraction. So in this form, it doesn't meet the technical definition, but if you rewrite this as an improper fraction, 3 times 4 is 12 plus 2 gives us 14/3. You see that, yes, mixed numbers are also rational numbers. It's an improper fraction, but you're still expressing it as a ratio of two numbers, 14 over 3, and the denominator is not equal to 0. But what about decimals? Would decimals be rational numbers? Let's think about this. Let's say that we have the decimal, the decimal 0.25. That sure doesn't look like a fraction to me. It doesn't have the form of a numerator over a denominator. But what is 0.25 actually saying? 0.25, if we don't read it 0.25, if we would give it its technically correct name, it would be 25 hundredths, wouldn't it? And how do you write 25 hundredths? Lo and behold, we have an illustration here that decimal numbers can be rational numbers. Now, what if we had this? What if we had the fraction 1/3? Okay. We know what 1/3 is. You cut an apple up into 3 pieces. Can you express 1/3 as a decimal number? Well, what does this mean? This means 1 divided by 3, doesn't it? I'm going to assume that you remember how to divide, and we have a pattern that we see going on here. No matter how many zeros we append here, we're just going to keep getting 3.333333. This is what we call a repeating decimal. We have a pattern here where it just never stops. So we have this. Let's look at this fraction. 25 over 100 is 0.25. Let me reduce this to lowest terms and switch it around. 25 over 100 reduces to 1/4. 1/4 is equal to 0.25. Let me go ahead and take a second to show that division right here. All right? 1 goes into 4. You know how to do this. 2 times 4 is 8. We bring down a 0. And our division is completed, isn't it? As opposed to this division here that goes on forever. And that's the difference between two types of decimals. We call one of them terminating and one of them repeating. And the difference between these two should be very, very obvious to you. 3. You know that 3. So the way that we indicate that, I'll explain this again in a moment. Terminating means to stop. Repeating means that there is a pattern that continues on forever. This is a terminating decimal. It stops. You get done with your division. This is a repeating decimal. You could divide from now until Jesus returns and you're still going to get 3, 3, 3, 3, 3, 3, 3. The pattern repeats. So decimals, there are 2 types of decimals that you can have. You must know this. You must be able to distinguish between them. Decimals may be terminating, they can be repeating. But you know what? There's another pattern or another way that we can have a decimal. Let's see if I can pull a good illustration directly from the text for that. actually I'm going to pause, put that off just for a minute, but they can also be non-terminating, non-repeating. So of course that means that you have a decimal can end. A decimal can have a pattern that is clearly recognizable, or you can have a decimal that it doesn't end and it doesn't have a discernible pattern. And we're going to distinguish between these two types go together. These are rational numbers. This third one here is an irrational number, because non-terminating, non-repeating decimals, you cannot write them as a ratio. So we say, and if you can't write it as a ratio, you can't write it in what we call fractional form, so they are not rational. Okay? Lots of vocabulary in this. You've got to make sure that you look through your lesson on this, and that you do your best to understand what's going on. This is truly something that as you work with the numbers, it will make more sense to you. Okay. We've talked about rational numbers. They're the ones that can be written as a ratio so that they look like a fraction. But we see other numbers that, and I'm going to look at our book at the bottom of page 48, that we have numbers that cannot be expressed as a fraction. And these are called irrational numbers. Here's an example. Pi is an irrational number. And when you learned how to work with pi, pi showed up in formulas like pi times the diameter was the circumference of a circle. And you learned pi, but you probably said, we're going to use, if we want to find the circumference, and we're going to use 3.14 for pi times 2 inches. And then the circumference of that circle was going to be 6.28 inches. But what you didn't know is that pi is not equal exactly to 3.14. Pi is actually 3.14159268337, I think, on and on and on and on and on. There's no pattern here. No pattern that repeats. It's just random as can be. This is what we call non-terminating, non-repeating, or irrational. Square root of 2, the square root of 8, all of these are irrational numbers. They cannot be written as a ratio of two numbers. So if you're going to actually work with those numbers and calculate, you come up with an approximate value for what they're equal to. Now if you look at example 4 and example 5, this says give rational numbers that are approximately equal to pi and to the square root of 2. Use your calculator on these for my class, page 49. And then example 5 says what numbers are rational here. Rational can be written as a fraction. I'm giving you explicit permission to my ARC kids. Use your calculator on this part of your homework. Use your calculator and say, what is the square root of 3? And study your books. I'm not going to go through trying to lecture this. The video would go on forever and your eyes would be glazing over. Try and work through this on your own. Send me a text if you've got questions, or we'll go over it in class. I do want to go on again, though. back to the different types of numbers, they have what they call a Venn diagram where you have circles and where you need to be able to identify if a number is a natural number, a whole number, an integer. And this is something they're going to want you to do in your homework. Remember, we started with that tree at the beginning. We had complex numbers and irrational numbers. So we're going to come home after class. So we have complex numbers and irrational numbers. Over here on the right, we have rational numbers, real numbers, integers, whole numbers, and natural numbers. And you're going to see that those will fit inside of circles. The smallest circle that you have would be your natural numbers. And those would be the numbers that you naturally count with. When you add a 0 to that, this becomes the whole numbers. You add the negative integers, well, the negative counting numbers, if you will, and now you have the integers. And then when you add all of the numbers that can be written as a ratio, you have the numbers that we call rationals. So we have the rational numbers. And then outside of that, all of this here, in this rectangle here of the board, these are real numbers. And these are the only types of numbers that we're going to be working with in Algebra 1. Now, if we had another leg on top of this, the complex numbers would be outside of this board, and the imaginary numbers would be over here on the wall to the right of the real numbers. But these are the only types of numbers that we're going to be working with in Algebra 1. And they want you to be able to say, let's say if we had the number 5. What is the smallest number where that number 5, smallest Greek where that can be? Well, is 5 a rational number? Yeah, it can be written as 5 over 0. Is it an integer? Yes. Is it a whole number? Yes, 5 is a whole number. But at its smallest, most specific point, it's a natural number. It's like saying, let's put dachshund. I learned how to spell dachshund because I learned that word reading, so I thought it was dachshund. Well, and then I learned it was dachshund. Let's say that this whole thing here is dogs. Is the dachshund a dog? Yes. Is it a little dog? Yes. Is it typically a brown dog? Yes. Does it have floppy ears? Typically, yes. Does it have short legs? Yes. So, it's true that the dachshund would fit every place within these circles, but its most specific definition would be here in the center circle. So that's what we're going to do with the numbers. Now, what if we had a 0? A 0 is a rational number. It's an integer. It's a whole number. Is a 0 a part of the natural numbers? No, 0 is not in there, so you would put your 0 here. And then, what if they wanted you to show where the smallest circle that a negative 4 would fit? It's rational, negative 4 over 1. It's an integer because it's a negative number. Is it a whole number? No, it's not a whole number because the negatives are not included in there. So your your negative 4 is going to go into your integers. 4.53, that would be a rational number because you can write it as a ratio. What would it be? 453 over 100. But something like we just talked about, we said the square root of 5 or pi, square root of 2, those go outside. They're real numbers because you cannot express them as a ratio. But what about the square root of 2? Square root of 4 is actually 2, so perfect squares are rational. Square roots that are not perfect are irrational. Okay, do your best to work through section 2.1. You have explicit permission to use your calculator on this. There's no reason for you to be having to calculate all of this stuff by hand. So work on those, text me if you really get stuck. We'll talk about it in class on Friday also. Have a good week. I'll see you next time.
What'd you say?